Cut.
Welcome to Group 17's video on parametric curves and their calculus, brought to you by us three. Get go! In this presentation, we will go through 5 different levels of definition and examples, calculus applications, application in circular motion and computer graphics, as well as references. Now let Zuyang guide you through level 1.
Thank you for your presentation. So today I will be talking about the definition and application of parametric curve in calculus. Next slide, please. So you can see that on the right is a picture of a curve. Now, if we want to express it on the xy plane, then using explicit function, we will come across the problem of the vertical line test. So if we do not want to fail this vertical line test, we need another way to circumvent it. And to do that, we use another variable t to express x and y. So such equation is called parametric equation, and the set of point x and y expressed to t is called the parametric curve. A specific type of parametric curve we want to discuss today is called the cycloid. So imagine a wheel with a spot of paint on top of it. If we roll the wheel in one direction, the motion of the spot of paint forms the cycloid. In the next slide, we have a formal definition of a cycloid for anyone who is interested in it. So next slide, please. If you are interested, you can see it. So now we move on to the usage of parametric curve in calculus. So there are 2 main usages of it, including finding the tangent line and calculating the area. Finding the tangent line of the parametric curve is a bit more complicated. Since the slope, we need to find the slope using the derivative of y over the derivative of x. Then we can find the tangent line normally, like with normal curves. For calculating the area, we can see that sometimes the area enclosed by the parametric curve is repeated. So we only need to calculate a section of it, then we can multiply it with a number. So thank you. So we will now move on to the following section on circular motion.
Yes, thank you, Zuyang. Now I'll explain to you how parametric equations are useful for describing the position of an object moving in circular motion. The purpose of this is to simplify equations describing position by introducing a common parameter t. Specifically, t here stands for time. As t changes, the values of x and y inform us of the object's exact position. X and y can pose as periodic functions of sine and cosine. X can be a sine function and y a cosine function, or vice versa. Let's examine a hypothetical situation where J takes this Ferris wheel in 5 minutes. From the direction that y changes, we can determine that it is a minus cosine function with an amplitude of 50 and a vertical shift of 53. The angular speed omega is equal to 2 pi over 5, so we can assemble the equation for y as you can see on the slide. On the other hand, x is determined to be a minus sign pattern, so the equation for x is what you can see on the slide here. Supposing that J has been on the wheel for 2 minutes, substituting t equals 2, we can have J's position, as you can see on the screen. Now I'll be passing over to Naman.
The relationship between x and y can be represented in explicit, implicit, or parametric formats. But the parametric format is the most suitable one for animations on computers due to 3 reasons. First, we do not need to know the relationship between x and y beforehand. Second, computers can easily calculate x and y values from the parameter t and then plot them on the graph. Last, we can easily do complex graph transformations with parametric equations. Here are some examples that can be animated on computer using decimal with that parametric equations on the screen. Here's the flower curve, the donut curve, or even more beautiful, the butterfly curve. We couldn't do this without referencing these resources.
And that shall conclude our video. Thank you for listening. And do you have any questions for our group?